Hi, good afternoon, and welcome back to the session wherein we're going to be looking at, the next unit in Foundation Diploma in Engineering. And this particular unit that we're looking at covering would essentially be, related to electricity. Now, one of the things that we need to look at in terms of the unit and its study would be to start from looking at a bit of an introduction and what all we are going to cover in this particular unit. Now, this particular unit, electricity, is intended to help learners develop and apply some knowledge related to alternating current and direct current, AC or DC, circuit theory in relation to circuit design. When we do talk about, anything which is mechanical and has some sort of a circuitry. Now, here, your main aim would be at the foundation level to learn some fundamental principles of electricity and electromagnetic radiation. Now, in order to do so, we have three learning outcomes that we're going to be looking at covering. The first learning outcome will look at and helping you understand the basic functions of electrical components within circuit. The second, and it has three assessment criteria. We'll be looking at covering things like topography, components, some various important components of electricity which allow us to create an electric circuit like resistors, capacitors, light emitting diode, transistors, inductors, and we learn about the integrated circuit. We'll also be looking at how the electrical connections flow, or how electricity in general flows. So we'll be looking at conventional current direction, we'll be looking at current versus drift speed, and obviously the nature of flow. And then we'll be looking at understanding what are the units in which electricity is measured when we look at talking about volts, voltage, and that all we'll be looking at covering in learning outcome 1. In learning outcome 2, we'll be able to look at applying some of the things that we've learned in learning outcome 1 to put to use in understanding how do we look at applying the basic principles of electricity that we've learned and the units to apply them to alternating current and direct current, AC and DC circuits in relation to learning outcome 2. We'll also be looking at, some of the important concepts like Kirchhoff's voltage, laws, and obviously some of the laws which do apply when we talk about electricity and look at implementing the principles of electricity and electrical circuits when we do conduct, experimentation and obviously design electrical or mechanical circuits wherein electricity is used. The third one would be focused on understanding, the basic bits of, I would put it this way, power supplies. And, when I say power supplies and power protection systems. So here in this case, what we are looking at is primarily going into understanding what are the different types of, current types. In some countries, we use AC, and in some we use DC. What are the voltages, 110 versus 220? And in some cases, the idea would be to try and understand a labeled block diagram of an electric circuit, which basically has all the important components of how electricity can be controlled, stabilized, and obviously seen moving through an electrical circuit. The assessment of this would be done through an assignment, and some parts of the task in the assignment brief are going to be practical. Now, in order to discuss the three learning outcomes, we'll go through some of the presentations and slides that I've created, and each of the learning outcomes and the assessment criteria will cover some of the key topics that are given in the indicative content in a bit of detail. So let me move you over to the slide that I've prepared, and we'll start off with the concept of electricity. So give me just 1 second. So in this presentation, we are looking at understanding some of the key components which are related to, electrical components of electrical circuit in general. Now, before we go into this, what I want to also look at is give you a bit of an introduction in terms of, what is electricity in the context of engineering. So when we do talk about electricity in the context of engineering, what we are referring to is the presence and flow of an electric charge. Now, this is the fundamental form of energy that we see as a backbone of most modern technology. So you have a circuit, and through that circuit, some sort of an electric charge moves, and that charge basically enables to be powered up, or tools and various parts the laws and mechanisms of how we can look at controlling electricity and controlling the movement of electrons. That's the important part. Controlling the movement of electrons through conductive material. Because obviously, electricity, sometimes you would come across this saying that, water conducts electricity, or steel conducts electricity, or cast iron conducts electricity, but wood and earth, do not conduct electricity. So, what we as engineers want to do is understand the concept through which we can utilize the fundamental principles of electricity. We can control the movement of electrons through conductive material. These are typically going to be metals, and this would help us generate, transmit, and then apply the concept of electric power to some of the tools and equipment that we are looking at uh, using in mechanical engineering. Now, there are key concepts when we do talk about electricity. These key concepts of electricity in engineering include things like electric charge. They would basically be the basic particles that experience a force, some sort of an electric force or a force, I would put it this way, and this force can be of two types, positive and negative. So normally when you look at a car battery, you have a positive terminal and a negative terminal. So just as an example for now, overarching example for now, what we will look at is when we look at the concept of electricity in engineering, we're talking about electrical charge, and charges are of two types. You have positive and negative charge, and there is no charge. It is called neutral. So electrons, which are negative charge, flow through conductors to create, or conducting materials or metals to create an electric current. Then we look at some of the basic, other units in which how electricity is measured. So we look at voltage, we look at current, we look at resistance, and we look at power. So when we look at voltage, the difference that we would look at in electricity or electric, when we look at potential energy between two different circuits, and the amount of pressure it applies to push those electrons out through a conductor, would be essentially defined as what is called voltage or electric potential. Now, when we do talk about current, these are certain standard definitions. What I would want to do is basically, put this as key terminology here, because this would help you understand some of the key concepts of electricity that we talk about in the context of engineering. So, what we would want to do in this case is understand what is current. Now, when we do talk about current, what we are looking at is, when we talk about current in general, we are looking at talking about a flow of electric charge, which is usually the electrons through a material. Now, that material has to be conductive. Generally, as I mentioned, it would be metals. And this conduction of electrons or electric current through the conductive material would be measured in what is called amperes. So normally when you look at an electric circuit, or when you pick up a appliance and you have an electric plug next to it, like your iron, or even if you look at your mobile phone charger and you look at the end plug of it, which you plug into the power out socket, you generally see that plug has some sort of an ampere rating. Now this is the rating in which you would see the flow of electric charge or electrons happening through the material, and this helps in powering devices, different types of devices at this moment, I would say, or different type of systems. Now, one of the other concepts that the equivalent force, that would be a force which will be called resistance. So there is an opposition to the flow of electric current within a material, and different materials and components show different type of resistance. Now, this resistance is measured in a unit called ohms. So at this stage, when we talk about resistance, and when we talk about the force which counteracts the electric current, would be called the ohm, and it is named after the scientist who actually created Ohm's law. And this is a formula which basically helps in calculating the relationship between voltage, current, and resistance in an electrical circuit. So just keep that in mind. This is something that we will come across and we will look at, is Ohm's law. And Ohm's law is something which basically was proposed by the scientist Ohm, and he was a German physicist, George Ohm, and he proposed this particular law in the early I would say early 18th century. And this addresses the relationship between three different things: voltage, current, and resistance in an electrical circuit. So we'll come to that in a bit. But for now, when we talk about resistance, it basically is an opposing force that we get to see resistance. Now, we also talk about power, the rate at which electrical energy is consumed or converted into other forms of energy like heat, light, or motion is going to be calculated using a formula or a term called power. Now, power is equal to VI. V is voltage, and I is essentially the current, which is measured in watts or voltage. So essentially, when we look at direct current and when we look at alternating current, there are two units of measurements that we are going to get to see. One is going to be watts, and the other is going to be voltage. So watts, normally a simple example, if you can put your thinking hat on, you would generally see when you pick up a light bulb or you pick up a tube light in some of the Asian countries, you generally see some of the instruments having a wattage rating or a volt power or a current rating of which is defined in watts. So you have a 40-watt bulb, 50-watt bulb, and that shows basically the amount of electrical energy which is consumed in lighting the light bulb, and that could be defined in the form of watts. So these are some important terms in the context of electricity, in the context of engineering, but when we look at relating it to electricity. Now, there could be various many applications of electricity fields. There could be electronic engineering, mechanical engineering, and civil engineering. Now, these are different branches of engineering that you would be looking at, but because we are related and studying the foundation diploma in mechanical engineering or engineering in general, what is the context of electricity? It integrates electric motors and actuators in machines and robotic systems to convert energy into mechanical motion. So when we talk about the concept of electric motors or the passage of current through electrical circuit, what we would get to see is that certain type of equipment and motors would essentially then end up producing what is called a mechanical motion. So when we do talk about, say for example, the alternator in a car, when you crank, or say for example when you switch on in the olden cars, obviously now we have most motor cars or cars, essentially we push a button and it starts the car. But behind that, instead of churning a key, the concept is that it basically passes a current through the alternator that ignites the fuel in the internal combustion engine. The pistons compress the fuel, and it generates, and it then ignites. The spark plugs in the engine ignite that fuel when it is highly compressed, and that compressed fuel produces energy, and that energy is converted into what is called mechanical motion. So in the context of electricity in engineering, what we would look at is, in this unit, we would try and extend some of the basic principles that we know about electricity and look at including complex topics like electromagnetism, alternating and direct current, circuit analysis, and electronic component design, which is the whole aim of actually studying this particular unit. So it is related to gaining and understanding, I would say, and building some knowledge, fundamental knowledge about the principles of electricity and electromagnetic radiation. So that, I hope, gives you a comprehensive introduction of this particular unit. Now, let's look at some of the assessment criteria that we're going to be looking at covering in Learning Outcome 1. One of the first assessment criteria is it talks about describing circuit typography or topography and their effect on the components. Now, one of the things that I would want to do is look at, getting into details in terms of understanding what is, the circuit topography. So let's look at understanding what is circuit topography. Now, let me bring a picture, just for the purposes of, better understanding. Let me just try and see if I can find a relevant picture from Google and try and see if I can include that for the purposes of our discussion. Yeah. So when we do talk about, circuit topology or essentially this particular part, what we are looking at is we are looking at understanding about what I would say is basically some sort of electrical circuits. And these circuits that we do talk about, would essentially be connected in some sort of a way that would allow the flow of electrons or essentially energy to flow through. So when we talk about circuit topology, let me try and see if I can bring this picture onto the slide. Just give me 1 second. Now, if you see this particular picture in general, what we are looking at is some sort of design, which is, created in the form of, I would say, circuitry that allows, current to flow. Now, just bear this in mind that it is some sort of a design or a circuit which is created to allow flow of electrons, which would mean that conduction of electricity can happen through a particular circuit. Now, in engineering, when we talk about circuit topologies or configurations, I would use that as a word, which is a better word, would refer to the arrangement of components within an electrical circuit. Now, each configuration would have an impact on how the current flows and how the voltage is distributed across various components. Now, when we do talk about circuit topologies or configurations, we talk about different types of circuit. The first circuit that we talk about is series circuit. Now, in series circuit, you would generally see components are connected with one after the other and in a single path. So if I try and let me see if I can try and bring a picture of a series circuit. And that series circuit would essentially be, a circuit like this. You would generally see this is like a series circuit. And in this case, what we're essentially seeing is that in series circuit, components are connected one after the other in a single path. Current would flow through each of the components sequentially. That is the important part in terms of series circuit. Current would flow sequentially, meaning that there is only one path for the current. So in this case, from battery, the current would flow to resistor 1, then resistor 2, resistor 3, and then come into the negative side or the other side of the part of the battery. Positive, it flows from positive to negative. Now, there are various components in this. One is current, which is the same current which flows through each component. There is voltage, because obviously the current would be measured in terms of the unit called voltage. Now, voltage drops across each component based on its resistance. What is the resistance the resistor would offer in terms of letting the current flow freely through its components? So this can reduce the current flow overall. And then if the component fails, obviously if the resistor is broken or if there is a broken wire or things like that, then the entire circuit would stop working, since there is no way the current could reflow or take an alternative path. And that is what generally the serial circuits would mean. Now, here, when we look at serial circuits, one such application that you will generally see very close to countdowning for Christmas. So you generally see in Christmas lights, each of the bulb is a part of a single lead or electrical wire to which it is sewed. And then in a simple circuit, one lights up, the other lights up. And if one of the bulb in the wire fuses, the entire lights that we see onwards from that bulb actually switches off, because this is a simple circuit where uniform current is desired to be flowing. Now, when we talk about second type, we look at parallel circuits. Now, when we talk about parallel circuits, in parallel circuits, what we do get to see is the components are connected across common points on a junction. And this would allow, the current to, I would say, flow through multiple, parts. So if I would look at a parallel circuit would look like this, right? Now, a parallel circuit essentially would mean that in this case, you would generally see that a series combines different resistors in terms of how the current is going to flow in parallel branches, but it remains same for each of the component within the series. There's no flow, unequal flow of current. Now, here again, when we look at current, voltage, resistance, and failure, here the parallel circuit is slightly better than the series circuit, but because it offers partial redundancy. That means that some part of the circuit may continue to fail. Even then, you would generally see some sort of electricity flowing through the circuit because parallel branches not all the parallel branches would fail. Now, here, if I have to look at parallel circuits, an example of this would be it could be used in complex computer systems or networks, wherein if one computer fails or if one hard drive fails, generally you would see this in data centers. You would generally see that the backup drive or drives which are connected in parallel would essentially provide the data or the data retrieval. So when you look at Google data centers, they have the same data being stored across different data centers. So if one of the data centers fails because of no electricity or because of short circuitry or because of whatever act of vandalism or something like that, there is a mirror image of that stored in other hard drives, and that would allow the distribution of data to continue if somebody was to place a query on, say, a Google Chrome browser. So here in complex systems like computer networks, you would generally see automated electric systems and power distribution systems where you would see both reliability and control over current flow, which is required. And that is why you would generally see parallel circuits. Now, the third type could be something that we would look at, what is called, series and parallel circuit. Here, we could look at combination of series and parallel circuit, and in certain cases, when we do look at combination of series and parallel circuit, you would generally see that this would be, say for example, also possible. And when we do talk about these, there are certain rules that would need to be followed when we conduct circuitry in which both serial and parallel types of circuits are used. So components in this case that are being used to design these circuits would need to be of the same voltage, and in this case they would also not differ in offering various resistance values. So in some cases, when we do talk about an example of parallel circuits, what you would generally see is that here when two lamps are to be connected one behind each other, you would generally have a parallel and a series circuit, wherein an example of a parallel circuit would be that a branch branches into two branches and then merges again, but that has the lamp on each of the two branches. So if let me try and bring a picture here to explain that, and what you're going to see in this case would be that here this would basically be what is called series and parallel circuit. Now, sometimes we do see that we use both of them together, and when we do experiments specifically in labs and other places, you would generally see that sometimes both these circuitry is combined. So here, if I connect a battery and a switch and two bulbs, this is a series circuit because they're connected one after the other. That means if the electric current flows in this direction, you would generally see if the first bulb lights, then the other bulb lights and the current gets completed and the circuit gets completed, the flow of the current gets completed, and that's why both the bulbs would glow. But if the first bulb fuses, the current would not go from here and the second bulb would not light up at all. So in parallel circuits, you will see that we connect them in such a way that the same type of current is flowing through two types of circuits, and that would allow, you know, both the bulbs to be lighted up. Even if in some case, if one is fused, the other bulb would still light up because it'll allow the current to flow parallelly to complete the circuit, and that is where you would see that this would essentially, work. Now, the next type of configuration that we get to see is what is called the, star, Y, and delta configurations. Now here they are commonly used in what is called three-phase power systems. So you have star, which is Y, and delta, which is the triangle. And what you're generally going to see, if I've covered that in the next slide, star and delta, what you're generally going to see is that here the configurations connect load and transformers in a specific way to balance and manage the high voltage systems. Sometimes you would see that when we do connect equipment or appliances which require three-phase electricity, just as an example, in the Middle East and in certain tropical countries, what you are going to see is that most households typically have two-phase power. But in some places, when factories and industries wherein they are running 24 hours, they are running heavy loads, what you're generally going to see is that they would have what is called a three-phase connection. And the three-phase connection would require typically in this case, the load that we get to see being used in terms of power being generated and the voltage and the consumption in terms of power being done and the resistance being applied requires three different phases of electricity, and in such cases you would generally see star and delta configurations to happen. Now here the main part is the application tends to be that you are going to use this configuration for transmission purposes. That means you're going to store electricity in transformers, and then when we look at electricity flowing from grids across to homes and factories and stuff, you'd normally have this configuration because the electricity would need to be stored and then transmitted using transmission lines, and that would mean that the circuits would need to be created wherein it does not allow or have too much resistance, which means that the electric current and the current or flow of the current would happen in an evenized form. So these components, when we talk about star and delta configurations, you're looking at a three-phase power system wherein star and delta configurations can connect or connect loads or different types of transformers in a specific way to balance phases and manage high voltage systems. Now, these applications are normally, this circuitry or this particular type of circuitry is normally applied in, industrial oblique motor applications where high power and reliability is required. That means, you're using something for 24 hours, three shifts, and you would want reliability in terms of machines and, the current and the efficiency to happen. Now, one of the last things that we will look at in this case would be something called the, T configuration. Now, when we do talk about T configuration, what we are talking about in terms of T configuration is that in this particular form of circuitry, you would generally see T or terminal configuration is an is a configuration that would generally be applied when we talk about a circuit design, which is often used to describe a specific arrangement of a component, such as transistors, capacitors, inductors, in a T-shaped form. Now, this configuration can impact various electrical characteristics in terms of circuit, impedance, and voltage. But generally speaking, when we do talk about this type of design or circuitry design, we are looking at a specific type of circuitry which is going to be designed in the T shape, and this would essentially be used to produce two-phase electric power. Now, this was essentially, um, I would say, if I would put it this way, that when we do talk about T configurations, we look at they having being used primarily in what is called two-phase systems, and in such cases, what you would generally see is that these systems would be used for, I would say, you know, configuration and distribution of electricity amongst components to balance off the usage in terms of, load sharing or load balancing, as we would call it. So when we do talk about T configuration, it is something which was, applied to the Scott T transformer, and this is a type of a circuit which is used to produce, as I mentioned, two-phase electric power. And in some cases, this allows, I would put it this way, the even distribution of balance or load between phases, which is different phases or sources of electricity. So I hope the first part of the assessment criteria, which talks about different circuit topology, is quite clear. So if there are any questions, feel free to ask me through the chat route, or you can stop me during the discussion. Now, the second part that we look at is primarily talking about assessment criteria, is talking about identifying the range of components and conventional symbols that could be used within when we talk about, electricity. So here, what we are looking at is that when we talk about electrical engineering, understanding various types of components and their conventional symbols is crucial for us to be able to read and understand different types of circuits and circuit designs. So when we do talk about various components, let's look at, first, what are the various components? Now, first type of component that we talk about is a resistor. Now, the resistor is basically a passive two-terminal component that resists the flow of electric current. It is often used to control the amount of current or voltage which can be passed through an electrical circuit. Now, here the function of the resistor is to limit the flow of current and control the voltage within the circuit. Now, this symbol is normally a zigzag line, which is an American symbol, and the European symbol is more of a rectangle. So just keep this in mind. What is a resistor? What is a symbol? And how do we and where do we use it? And what is it is used for? The second part that we talk about is a capacitor. Now, the capacitor is essentially a two-terminal component that stores and releases electrical energy in an electrical field. Now, this could be used to store energy, it could be used to filter energy, it could be used to pass electric current or electricity, at various timings within the circuit. Now, the function of the capacitor is essentially to store and release electrical energy. It smooths out fluctuations in power supply. Now, in the olden days, I don't know whether I would say olden days, but now as well. But in the olden days, generally, what sometimes we ended up using were something called devices called transformers, and these transformers were connected to refrigerators or certain important type of electrical components which could be damaged if the flow of current is not even, or if there is a lot of fluctuation in the flow of current within these components. So here the transformers were created and they have components called capacitors which basically help in controlling the fluctuation in power supply. Now the symbol is like two parallel lines with one shorter and the other indicating the, basically one indicating the negative side, and these two parallel lines are of the same length. That is what you need to keep in mind when we talk about capacitor. The third type is what we call light emitting diode. Obviously, we can also say a diode first, but then there's a light emitting diode. Now, the diode is essentially, if I talk about it, allows current to flow in one direction only. So as you can see, the direction of the arrow is pointing from left to right. This is the direction in which the current will flow. It acts like a one-way gate. That is a diode. Now, a symbol is normally a triangle with pointing lines and the triangle side being the anode and the other side being the cathode. So when we look at two different other components within a diode, we'll be looking at anode and cathode, and we'll come to that in a minute. Now, when we talk about classification of a light emitting diode, this is a semiconductor device that emits light when current flows. So sometimes we do see lights which have, which beep or which emit some sort of electricity when the current is flowing. That is to show that emitting light showing that the current is flowing through it in the correct direction. And here the symbol of the diode or the light emitting diode is the same, where the arrow is pointing outwards to indicate these two arrows emitting, pointing outwards to indicate that the light is being emitted. Then we talk about transistor. Now, transistor is a semiconductor device that amplifies or switches electric signals and currents. Now, this is fundamental to something called modern electronic circuits. Now, the function of the transistor is that it amplifies and switches electrical signals. Now, there are two types, NPN and PNP. So when we talk about NPN transistors, a circle with three connections showing an arrow pointing out from the emitter. And when we talk about PNP, it is similar to NPN, but in this case, the arrow is pointing inwards towards the emitter. So here you would see it is pointing outwards and here it is pointing inwards. Now, the next type that we look at is basically called the inductor. Inductor is essentially a passive component that stores energy in a magnetic field when current flows through it. Inductors are used to control and store energy or filter energy and obviously do signal processing. And the symbol is normally three, I would say, peaks essentially alternating like half circles. Then we talk about, things like there could be other things like switches, batteries, fuse, ground, transformer, relay. You could have an integrated circuit and you could also have a motor. Now, when we do talk about integrated circuit, this is where all these components come together. And in a way, in engineering, we solder these components across to create a circuit. So you'll have a resistor, you'll have a switch, you'll have a battery, you'll have a fuse, you'll probably have a transformer, light emitting diode, inductor, capacitor, and all these components could be put together into something called an integrated, circuit design. And this integrated circuit would essentially then, do a particular function or perform a particular function. And that is what we say when we do talk about integrated circuits. So in this assessment criteria, we are talking about identifying the range of common electrical components and their conventional symbols. So we could have lots of other different types. As I mentioned, you could have a transistor. Sorry, you could have a switch, a battery, a fuse. You could have, a couple of other components, and these could be something which I can put here just for the purposes of, if you want to look at studying them in a bit more detail. Because at the end of the day, when we look at constructing a circuit, some of these, would be bits that you would end up using. And that is where these are different types of components that can be used primarily for the purposes of creating what is called an electric circuit or an integrated circuit. So let me just put this other slide as well, wherein I want to cover them extensively. And all of these components have symbols, and they have, or they play a particular function when you use them in the construction of what is called a circuit. And that is what we need to understand when we do talk about various components and symbols within, I would say, within electrical systems. So that's the I would say, the second assessment criteria. Now, one of the things that we also want to look at is we want to look at electricity flow conventions. Now, these conventions are important because of the fact that these conventions essentially represent electrical circuits. Now, there are three different types. One is conventional current direction. Conventional current assumes that positive charges flow from higher voltage to lower voltage. And this is established before the true nature of how electron flow, which is how the laws of electricity were understood. Now, the other one is current versus drift speed. Now, electric currents normally, is a movement of charged particles, which are electrons. Now, how the actual drift of these electrons happens, whether it's happening slowly, whether it's alternating, whether it's flowing or propagating, where the current is slowly increasing, is almost dependent, on how and where they are moved and designed to move in the circuit. But electrons, which basically generate electricity or carry electricity, typically move at the speed of light. That is what you need to remember. And the nature of charge flow. So electrons are the primary carriers of electric current or and charge, and they conduct electricity from negative to positive side. So what we do learn when we do talk about some of the electric laws in general, in when we do talk about electricity laws, and when we talk about, we'll be looking at, say for example, the German physicist Ohm's law, and we'll also be looking at Kirchhoff's law. Then here is where what we are going to be looking at understanding is that how is the flow of electricity determined, what kind of circuits we can build, and when these circuits are built, where and how would the charge or the current in terms of voltage or watts would flow, and how would that create some sort of mechanical motion in the context of mechanical engineering. Now, the last assessment criteria in this particular unit talks about describing electrical current and what is the potential difference between electrical current and potential, and how it moves. That is what we want to be looking at. So when we do talk about electric current, as I mentioned to you earlier, it refers to the flow of electric charge through a conductor. Now, conductors typically tend to be metals, and the movement of electrons from one point to the other actually helps in the conduction of electricity. Now, electric current is generally measured in what is called amperes, which is the unit which is used to measure electric currents, and it represents the rate at which the charge flows at a given point. The symbol is normally for this is I. So when we talk about ampere, A is the symbol, and when we talk about charge flowing past a given point, the symbol is going to be I. Now, when we talk about potential difference, that is what is called voltage. Potential difference is referred to as voltage because it's the measure of energy being carried by the electric charge as it moves between the 2 points in a circuit. So from negative to positive, or positive to negative. Now, it represents the amount of work which is done per unit charge in moving that carrier between those 2 points. And potential difference measured between 2 points. Symbol for essentially let's say, relationship between electrical current and potential difference. That is what we need to look at in this particular assessment criteria. So as long as you understand that electrical current is the flow of electric charge, which is typically the form of electrons through a flow of electrons through the current, and it represents the rate at which it moves, and the rate at which it is measured is called amperes. Now, potential difference is often referred to as what is called voltage, and this is the energy difference between the unit charge required to carry that between 2 points in an electrical circuit. And the measurement unit for this is what is called. About the relationship between the two, let me insert a slide. So as I was explaining, when you look at the relationship between current and potential difference, this is what is called the Ohm's law, and V equal to IR, that is the Ohm's law. V is the potential and is typically applies. When I say, if I put it this way, this is the law which basically applies and explains the relationship between, you know, um, current and potential difference. So given the resistance, the increase in potential difference results in the increase in current and vice versa. So if the resistance increases, the difference in current flowing between the circuit increases, and if it decreases, then the difference is that the current flowing through the circuit decreases. Now, understanding both the current and potential difference is obviously very essential, because within these circuits can essentially be removed. So what I've done is I've basically explained this in one or two slides here so that you are able to understand what is the relationship between electric current and the first assessment criteria, which is understanding the basic functions of electrical components within the circuit. And I've augmented the presentation. And obviously, when you look at the second lecture, we'll be going into applying some of the things that we've learned here to create circuits which are going to carry को बंद कराना पड़ेगा यार, मेरा ये बार बार इंटरनेट डिस्कनेक्ट हो रहा है। वो चले गए ऑफिस से। मौकम मौकम एक छोटी सी प्रॉब्लम है, आज इंटरनेट में प्रॉब्लम आ रही है। मैं अभी जब सेशन कर रहा हूँ तो मेरा जूम बार बार कट रहा है, तो तेरे को 10 मिनट के लिए बंद करना पड़ेगा अपना, क्योंकि मेरे को सेशन रिकॉर्ड करने हैं बहुत जरूरी। मैंने एक कर लिया है, यू कैन गेट बैक ऑन टू इट इन नेक्स्ट हाफ एन आवर, नॉट अ प्रॉब्लम। बट मेरे को अभी चाहिए, मेरा 2 बार सेशन डिस्कनेक्ट। Let's say relationship between electrical current and potential difference. That is what we need to look at in this particular assessment criteria. So as long as you understand that electrical current is the flow of electric charge, which is typically the form of electrons through flow of electrons through the conductor, and it represents the rate between 2 points in an electrical circuit. And the measurement unit for this is what is called